So welcome everyone. Do you guys remember where we stopped last time? Yeah, it's all in a blur. Okay, no idea. So we finished particle in the box, right? Remember something about particle in the box? Very useful model. And what I showed is that, well, the main equation that we're trying to solve in quantum mechanics, whether you're dealing with molecules or other systems, it's time-dependent Schrödinger equation, right? And for Hamiltonians that are time-independent, it turns out that we don't need to solve this equation. We can obtain its solution from the solution of so-called time-independent Schrödinger equation. Right? So time-independent Schrödinger equation have multiple solutions, and we can use them to obtain the solution of time-dependent Schrödinger equation. So if we know this, we know Hamiltonian, presumably. And so what else do we need to go from time-independent to time-dependent picture? Yeah, initial conditions, right. So once we know the initial conditions, that's our starting point. Essentially, we need to present our initial wave function. So it's like an initial trajectory or initial velocity, right? So in the quantum mechanics, we only need to know the wave function, but it's more complex object than the position and momenta. So then we express it as linear combination of solution of time-independent Schrödinger equation. These coefficients can be found very easily if you know how to integrate, right? And then that's what Fourier left us as his heritage. So Fourier taught us how to obtain the coefficient in this expansion. And once you know this expansion, the solution of this equation is very simple. It is essentially just you use the same expansion and you add these exponential factors, right? So that's the solution for time-dependent. So for that, you need solution of time-independent and initial conditions. So this is not a trivial problem to solve. And we solved it for particle in the box. Right? So we solved it for 1D up to 3D. So we saw that it's increasing the dimensionality doesn't really pose much of the problem because the Hamiltonian of three-dimensional problem is just the sum of Hamiltonians for one dimensions. And we know how to solve individual problems. We know how to put them all together. This is separable Hamiltonian. Please ask questions if you don't follow some of the stuff I said, because that's kind of more fast-forward review version of what we've done already. So at this point, I think everyone is comfortable with what I'm saying. If not, don't hesitate to stop me and ask. I will be happy to explain more. But this is kind of our stage. And at the end, last lecture, I think I promised that, or we consider so-called variational principle, variational approach, is next thing to consider. And so this is all for essentially solving time-independent Schrödinger equation for general problems. Like as an example of a general problem, I gave you a particle in a box where we have a linear potential instead of flat bottom, right? So normal particle in the box has a flat bottom, right? So potential is exactly 0 when you are inside of the box. And this problem has a potential which which has a linear dependence on the coordinate, right? So whenever you go from the left side to the right side, your energy goes down. It's like almost like a, imagine this room with the floor being skewed to one region, and so you would, well, probably guess intuitively that most students will be on the side where the energy is lower, right? So all the tables will be sliding potentially to the lower kinetic energy, and so things will be more concentrated here. Now, this is all intuitive considerations, and the question is, but how do I solve even in 1D with this potential? So the Hamiltonian would be kinetic energy plus potential energy as usual. How do I solve my time-independent Schrödinger equation? And the answer is there is no analytical solution. In a sense, there is no, I'm not aware at least, way of writing solutions of this equation with this potential as some kind of sine functions, cosine function, those sort of functions, the analytic functions, right? And so, but what helps is variational principle, which we proved last time. And variational principle says that if, say, you create such energy as you put any random function phi, the Hamiltonian, the same function phi, divide by phi, right? So here phi is any trial, it's called trial function. You can substitute trial by random, anything you want to put there, any trial function that respects boundary conditions. By boundary conditions, what do I mean is that the function must be inside the box, right? Because we know the potential is infinite outside of the box. If you put there some function that has non-zero value outside of the box, right, then you'll get infinities, and no one wants to work with infinities. But even kind of with infinities, still the statement will be correct that this energy will always be larger or equal than the true energy of the problem. All right, this is for any phi is any trial function. Okay, respects boundary conditions, and so we assume that E1 is the lowest of all infinite number of solutions of this problem, right? So we have true solutions. The E1 is the first one, the lowest one, and we just organize them that way. And this theorem of variational principle says that no matter what function you put here, the energy that you get out of this expression is still going to be higher than the true energy, right? So that's what we proved by doing the expansion of this phi function as a linear combination of the true solutions, which we don't know, but it turns out that we don't need to know them to prove that statement. That was, to me, is kind of a very remarkable fact that shows the power of mathematical thinking. Right? Okay, so now it turns out that this variational principle helps us to solve any problem in quantum mechanics, at least approximately. Okay, so that means we won't obtain analytical solutions, but we will be able to obtain the solutions which are very close or arbitrarily close. So you put more computational efforts, they will become closer. If you want them to be even more accurate, you can kind of just buy a more complicated or more expensive computer, put more efforts, and you can get to the solution of most of the problems arbitrarily close. Okay, so some of those problems, though, scale exponentially. So if you want to be really close, then the computational price goes exponentially high. Right? So, but potentially it's possible with the power of variational approach. So today we'll talk about variational approach. Variational approach. And that's a technique that is based on variational principle, or on this theorem, essentially. Okay? So what this theorem allows us to do, it allows us to essentially construct approximation. So say our function phi, and here I'm using more of my kind of physical intuition, and it's not really something set in stone, but one possible way of trying to approach these solutions of time-independent Hamiltonian equations, right? Time-independent Schrödinger equation, is to write the function phi as a linear combination of, say, known functions. And to have, okay, so let me define them as phi n's. Okay. And so what these functions phi n x will be, they will be solutions for particle in a box Hamiltonian. And these energies will be epsilons, different energies, right? So what I'm trying to do here is I'm trying to find a solution for problem of particle in a box with inclined bottom, right? So that's my Hamiltonian. And I'm trying to find this function as linear combination of solutions for the problem that I know how to solve. Okay? So this problem has Hamiltonian, which I define as a particle in the box Hamiltonian. I know how to solve this problem. If the box of the size L, then phi n x, you all know them. Square root of 2 divided by L, sine of n pi x divided by L, right? You've seen them, right? And the epsilons are n square pi square h bar square divided by 2ml square, right? So we know the solution for this problem. Now we will try use them to solve the problem that we don't know the solution yet. Okay? By using this construction. And what I'm saying here is that it's not a unique construction. You can potentially use some other form that depends on parameters. But the idea here is that I will turn this equation, right? What is this equation in terms of, is it algebraic or differential? Do you guys know in general, like there are algebraic equations that we study in high school, differential equations we study in universities. Have you ever heard? There is even course, differential equations. Yes, no? Yeah. You heard about differential equations, right? So Schrödinger equation is a differential equation or algebraic equation? Algebraic. Algebraic. Do we have a consensus on that? Yeah.
There's a differentiating operator.
Yeah.
Should it be differential?
So? There are two opinions. What about others? Do you guys have opinion, or doesn't really matter? It's a very simple question. It's like 2 plus 2. It's not equal smile. Okay? So what do you guys think? Differential. Well, so if you write down the Hamiltonian, right? So it has a kinetic energy, okay? And so kinetic energy is, for this simple case of, say, any one particle problem, it's second derivative, right? It's an operator that is second derivative. And so the differential equation, the hallmark of any differential equation is that you have a relation between a function and its derivatives. Okay? So algebraic equation, you have a variable usually, x or y, and so you have a relation between powers of x, right? So if I write ax squared plus bx plus c, right, which can be formally thought as a x into the 0 power, second, first, 0, gives you 0, right? So this is the relation between powers of variable. That's algebraic equation. And if you have relation between derivatives of the function and the function itself, then it's differential equation, right? So now solving algebraic equations are easy because, well, we studied that in high school. And solving differential equation is not that easy, and takes more effort. But what variational approach does, it essentially allows us to formulate differential equation, at least its approximate solution, as a different algebraic equation. Okay, so it maps differential equations to algebraic equations. So that's why it's so useful. It's so powerful because then, although it doesn't give you an exact solution, it gives you approximate solution through the solution of the algebraic equation. That's why it is appreciated now. Right? Okay, so now how do we do this? We can write down, by the way, we established that it's differential equation. Okay? It's differential equation because there's a relation between derivatives of functions and functions, right? Now, how does this...
Why is differential?
Because it has derivatives, right? So kinetic energy is a differential operator, and by definition, differential equation is equation that connects function with its derivative, right? So we have a connection between function phi, right, phi, and its derivative, because the kinetic energy is a second derivative of the function, right? So you can write this equation as some coefficient alpha, function second derivative, plus some function v times function and v minus e, phi equals 0. So, right? So this is a connection between the function and its second derivative. This is kind of what by definition we call differential operator. So algebraic equations do not have derivatives of functions involved. Okay. Or there is also so-called functional equations where you have function at, say, one point equal to some function, known function, say, multiplied by function in a different point. Right? So, and then you can try to figure out what the function is based on the functional relation. But that doesn't include any derivatives, so this is a different story. Now, how do we apply variational approach? How do we transform the differential equation to the algebraic one? I will illustrate that on the example of the particle in box with inclined bottom. So the way it goes is you can formulate what this approximate energy is by putting the function phi of x, h through h, right? Okay, and naturally, because phi contains coefficients and functions, but the functions we know, right? Phi n's, which are involved here, we know them. So the only unknown part in phi is this coefficient cn's. Right? So they are the only unknown components. Therefore, this energy that we formulated like this, it can be considered as a function of those coefficients, because the coefficients will go into every phi, right? So then we know that this energy, no matter what coefficients we put, will always be higher than the true energy, right? So now, in order to choose the coefficients in the best way, all we need is to minimize this function with respect to coefficients, right? So this is our problem. I promised you algebraic problem. Right now it's a minimization problem, and we'll get to the algebraic problem at the end. But tell me, how do we, if I give you a function, how do we find the minimum of the function? In, say, if the function is two-dimensional. Because we have many coefficients, so the best way to think about this could be some function like this. What's the minimum of this function? Presuming that omega tilde, they're more than 0, they're positive. And yeah. So how do we find the minimum? Function f with respect to x and y. Sorry? Derivatives? Yeah, what do you do with derivatives? You know how to form sentences, right? So you can actually say, I take derivative and do something with it instead of just exclaiming derivatives. So what do you do with derivatives? So you find the partial derivatives, right? There are two of them. Okay, and what do you do then? Anyone else? Yeah.
Set them equal to 0 and solve for x and y.
Okay, so both are 0, and you find x and y that that makes them, let's put x and y tildes. So we trying to find x and y that are making the partial derivative 0, right? Sounds like a plan. Now, the same thing can be done here, right? So if you want to minimize this function, because it is a function, this e is a function of coefficients. So all you need then is to find the partial derivatives, make them 0, and then find the coefficients that make this partial derivative 0, right? For any n, right? N can be anything, like essentially for all n's from this expansion, right? So small n runs from, say, 1 to big N, where big N can be 10 or 100 or whatever number your computer allows you to. Because at the end of the day, the problem that we will try to solve, it's solved on the computer. It's not analytically solvable. So for all n from 1 to big N, we want this to be true. Okay, good. So let's find this function, right? So in order to take the derivative of the function, we need to know the function. And here, what will help us is, again, the orthonormality of the particle in the box functions, right? And the fact that we can calculate some of the integrals, essentially. So if you put, instead of phi, the expansion, that would be some Cn phi n here, h sum over C k phi k here, just to make them independent, right? And Cn. And so then we can take the summation outside of the integral, and k. So this problem will involve real functions and real coefficients as well. Therefore, I will skip the putting the stars. They will not change anything. So from this point, I will consider all the quantities as real quantities. So these are two coefficients outside of these brackets. And then inside, we have phi n, h phi k. This is an integral that can be calculated because we know functions and we know the Hamiltonian. And here in the denominator, we will have also Cn ck. And the integral is phi n phi k. Can we say anything about the integral in denominator? Somehow simplify that integral. Yeah.
So it's 1 if n equals k and 0 if n is not equal to k?
That's correct. So that's kind of a manifestation of orthonormality. Does everyone see that? Things will go much faster if you say yes or no. Okay, good. Because I'm waiting, right? Okay, so if everyone sees that, let's proceed. I will, just as a short notation, instead of this, I'll just say h and k. This is the matrix element of the Hamiltonian. And so what I have here is energy is equal to sum of nk, Cn, Ck, Hn, Hk. These matrix elements, they are constants, so they do not depend on coefficients. And in the denominator, we have Cn squared. Because, as was pointed out, this integral here is either 0 or 1. It's 0 when n and k are different, and when n and k are the same, then it's 1. Right? That's why it kind of removes the second summation, leaves it like this. Now we need to calculate what will be the partial derivative of energy with respect to, say, some coefficient, right? And so coefficient can be anything. That's why I put a different subscript, m. N and k are kind of running indices. And so how do we differentiate the function that is a ratio of 2? I will call them f and g, right? So g is the denominator and f is the numerator. So then when I differentiate the function, which is a ratio, I need to differentiate the numerator multiplied by denominator minus differential of the denominator multiplied by numerator and divide by the square of the denominator, right? So you all have seen this equation, and this should be 0 because we're looking for minimum. By the way, when we equal partial derivatives to 0, we can find both minimum and maximum, right, of the function. Generally, this is a necessary condition, but not sufficient that all derivatives are 0. So you can have the situation like this. At the point of maximum, you have all derivatives 0. Or if you have a function like this, then in the point of minimum, you have all the derivatives 0. Also, you can have mixed states when you have more than one dimension. In one dimension, the function can be having maximum, and another minimum. That's so-called saddle point, right? So the fact that we are looking for 0 of the partial derivatives turns out that we will find multiple solutions for these equations, and only one of them will be true minimum. Others will be maximum and saddle points of a different kind, right? Now, back to this equation. Turns out that you can simplify it because since we're looking for 0, the numerator will be, it's enough so that numerator is 0. F prime g equals g prime f. Okay? And then from that you can deduce that f prime is equal to g prime f divided by g. Right? So we just move g on the other side. But f divided by g is our energy. So we can write that f prime equals to g prime times energy. And that's the condition for partial derivatives to be 0. Okay? Now we will find what f prime and g prime is and formulate the equation. So f prime is our partial derivative of df with respect to Cm, and it's equal to well, our energy, and then dg over dCm. Right, that's exactly the expression I wrote here. now using the partial derivatives. All right, so then df over dcm is derivative of numerator right? How do we differentiate that? Well, n and k at some point become m. That's why that's the only point where you can differentiate them. The rest, when n and k are not equal to m, then you have them like a constant essentially, and therefore this expression is essentially when you have one of them ck h and k Okay, so that is the situation where this is the case where both n and k are equal to m. So then we should have, since it's a square, we differentiate and it should be 2. And this sum comes out of the sum where only one term is, say, n or k, they're equal to m. And so since there are two indices n or k, so we also will have 2 in front of the such sum. Okay, so that's the result of the differentiation. And now when we consider denominator, the g over d cm. All right, so what is our denominator? It's the sum over cn squared, right? So what we have here is 2cm, because only one index is running, and whenever this index is equal to m, that's the only term that gives non-zero, cm squared. All other terms are considered to be a constants because we differentiate in respect to cm. And their subscript is not equal to m. All right, so this is essentially g prime, and this is our f prime. All right, and so our equation becomes two sum over k not equal to m, ck hmk plus cm hmm equals to energy multiplied by 2 cm. So we can cancel 2's and also rearrange this into, this is the equation that we obtained by differentiating the cm. Now it is possible to solve it. The solution I will illustrate on the situation where I consider only for simplicity, I will consider only two terms in this whole summation for the phi. So big N will be just 2. All right. Then we'll have two equations, dE dC1 equals 0 and dE dC2 equals 0. And what they give us is this type of two equations, C2H22 plus C1H11 equal to energy C1 and C1H21 plus C2H22 plus EC2. These are the equations. Now we have potentially C1, C2, and energy to find. And the small h's, all these four numbers. This should be 1, 2. All these all h numbers are known. Potentially, we can find them because we know the basis functions we're working with. And so for those who solved we have kind of C1, C2, and energy to find, three variables. Also, we know that because of the normalization condition, C1 squared plus C2 squared equals 1. That comes out of essentially expanding this to be 1. All right, so we have three equations, we have three variables, so we are good to go. So we can solve this system of equations and find what the coefficients are. Once we know the coefficients, we can find the energy and finish the problem, right? So in linear algebra terms, this equation are called eigenvalue problem because they can be formulated in a matrix form. H is a matrix, the coefficients here, and for those who study linear algebra, they know how to multiply vector by a matrix. That will be exactly the left-hand side. And in the right-hand side, we have energy multiplied by a vector. And so this is a standard problem. And if you use some kind of software like MATLAB or language like Python, then there's libraries how to solve these problems, even for larger matrices. Now you can see if you add more, C1, C2, these matrices can grow with the number of coefficients or number of terms that you include in your expansion, but they all can be solved, right? So you can just set up the matrix, and then the computer will find you what the coefficients are and what the energies are. Okay? So that's the idea here. This course kind of ideally would be taught to people who study linear algebra. Okay, and if you don't know anything about linear algebra, then just consider that you are getting these essentially algebraic equations, right, that you need to consider. C1, C2, those are one of the simplest algebraic equations you can find, you can come up with, because the H1 and with small h's, and they are known, right? And so then you just have many of them. That's why, but all of them are linear. So you don't need to even go to the high school to be able to solve them. Now the only part that is left actually is to formulate what the H matrix is. And in my notes, it's the given. So if we have a potential like this, and we put it inside where? Right, so somewhere here. Right, this is the integral that defines the small h. Right, then you obtain the expressions like, they're very simple to derive. It's just integration of known functions. And also the diagonal terms are slightly different. Okay. And in the notes, I also provided you with the results of calculations when you put when we put two functions in this expansion. You get I can just put them here. So with two functions in the expansion, we're approaching energy. So this is all going to be approximate, right? Minus 0.57, and that's n equals 2. Approximate value of 0.660 you get when you put n equals 5. So you put more functions, and then eventually, I guess the converged result is minus 0.6002 when you put n more than 10. Okay, so you can consider this as a ground state of particle in the box with inclined bottom. Naturally, since, by the way, I forgot to mention that alpha here is minus 0.1. So for the potential like this, essentially we have, and L equals to 10. So we have a box, and we have an inclination, so that compared to the normal particle in the box, that inclination lowers the potential, right, of the box, because alpha is negative, and that's why the ground state, instead of being positive, is actually negative. Because in the particle in the box, it's always positive number. Yeah.
Where did you get H and K? How did you get that?
This one?
Yeah.
This just following the definition, what I mean by H and K. These are the integrals where functions are known and the Hamiltonian is known, right? So Hamiltonian is the Hamiltonian of the problem. You have kinetic energy and the potential, right? And the functions are functions of particle in the box, sine functions, right? So you put this all in integral, and naturally, what do we have? This part, for the diagonal term, you can see the resemblance with the particle in the box problem, because it's just a part that comes out of kinetic energy. In off-diagonal terms, when n is not equal to k, n is not equal to k here, then there's no kinetic energy part, because kinetic energy, like the functions I'm using, they're eigenfunctions of kinetic energy. And if you consider the matrix element where k and n are different, then kinetic energy will generate some, since it's an eigenfunction, it will generate lambda phi k, and the functions are different, so they cancel each other, right? So they give you matrix element which is 0, so there is no kinetic energy part. This is fully coming from the potential energy part, okay? And the rest is just an algebra, okay? All right. So now we can solve problems like this, or with different potentials. Actually, with the variational approach, you can kind of consider the box with any random corrugated surface. So if you know what this function is, then you can find what the states are, essentially, by using the same approach. It's just you would need to calculate the integrals with the particle in the box function and this potential, right, to obtain analogs of the small h matrix, right, matrix of your Hamiltonian. Any questions? So this is really powerful approach, especially in one dimension. Going to more dimensions, it turns out not that easy, but let's kind of summarize things on the let's kind of finish the variational approach on a positive note, because in a kind of grand scheme of things, it's very powerful in 1D, but when we go to the more dimensions, it becomes more and more difficult exponentially difficult actually to apply this whole thing, because the matrices will grow very, very quickly, exponentially quickly. Okay, so now what I want to show you is this discussion we had in the first lecture, or sorry, previous lecture, about errors that are made in the textbook by Engel. So we'll talk about that, and now I'll show you how to address the problem properly. Okay. So these are some printouts from Engel's book. Let's see, full screen. All right, so what this chapter is about is applying the particle in the box for realistic problems. And let's see, can you read what is written there? Kind of. Okay. So I will read. Okay, I will explain what is written there. You just enjoy the pictures. And so the idea here is, we know this particle in the box problem very well now, and he shows very few examples where you can use it to understand how the systems that are not as simple as particle in the box behave, because the behavior is defined by so-called quantum confinement. So whenever we start making things smaller and smaller and smaller, that's what quantum confinement is that things cannot become infinitesimally small. Kinetic energy doesn't allow that. It's a second derivative, and when you squeeze the wave function, the kinetic energy goes up, right? So that's the piece of physics that particle in the box captures very well, because essentially all energy of the particle in the box functions, they're coming from kinetic energy. And the smaller the box you make, the higher the energies are. More than that, for the physical problems, generally, we are not interested in absolute energies, because absolute energies depend on where is your zero of energy. Okay, so this is arbitrary. We can say that the zero of my energy is when things, like in molecules, for example, in the calculations that you will be doing in the lab, zero of energy corresponds to all electrons and all nuclei to be separated from each other, right? So that is very kind of strange point, especially for chemistry, because for chemistry, when we talk about chemical bonds, zero of energy would be more natural to choose if we say separate atom A from atom B to infinity, right? So, but there's still atom A and atom B, say HCl, right? We separate H from Cl to infinity. That's our zero, and then we study, okay, how much energy do we gain when we bring them together? But but equivalently, we can say, all right, our zero is when we disintegrate atom H. So we take electron, we take a proton, we put them to infinity from each other. We do the same for every electron of Cl, and that's the zero that is taken in electronic structure calculations. Why? Because, well, they cannot make a special treatment for some molecule. They are making kind of unified zero for all molecules, right? And for all molecules, you can disintegrate them for electrons and nuclei, right? But the whole point here is that the zero can be quite arbitrary. Okay, so we should not really focus too much on the absolute values of energies. What is more important, what is more interesting, is energy differences that we probe with the spectroscopy, for example. And now back to the point here that one of the very interesting questions, at least to me, is that why some materials, they conduct electricity and some don't, right? So you know there are insulators, there are conductors, there are semiconductors, right? It turns out that particle in the box actually can be used to explain this very fundamental law of nature. And quantum mechanics plays a big role. Now, how is it done in Engel? It's done where things are oversimplified too much, to the point where they become nonsensical. Okay, and so that's what I want to kind of illustrate. That even Einstein has a quote that everything must be simple, must be made simple when you explain it, but not simpler. Okay, so that's the case where things were made too simplistic. When you're trying to make it too simplistic, then they stop making sense. Now, what's the starting point here? The starting point is we are assembling material from atoms. And say this is the potential of the sodium atom. So he considers the sodium as this typical case of conductor because it's a metal. And it's convenient metal because sodium can donate not 1s, but 3s electron, right, to the bulk of the material, right? And so there is this outer electron of sodium that experiences the potential of the nucleus. And when we take one sodium and bring another sodium, well, then the chemical bond is formed, and the potential for our electrons become these external electrons that are less attached to the core, right? They become kind of from such potentials of the separated sodium dimer to the unified potential, where the barrier is kind of getting smaller. Now, if you start like assembling more sodium atoms, right, together, then there is now you can understand how the work function forms. You remember when we were talking about photoelectric experiment, when we shine light on the, say, metal, then I was plotting this diagram of the potential and the electrons sitting in some kind of well. You shine some light, and then you can promote the electrons out of the metal, right? So essentially, this is like a build-up of the work function, the energy that is needed, so that electrons can escape from the bulk of the metal. That's this energy. But within the bulk, essentially, all the electrons experience this corrugated bottom of, as you can imagine, very big box, right? Because if you continue doing that, you are kind of getting the picture like this, where yes, there is some structure at the bottom, but overall it's like a particle in the box, of like very large box though. If you are talking about macroscopic sodium piece, then it's Avogadro number of atoms, and the box size is large. Now, the energy differences between the levels, here the equation is very simple. You can always calculate what's the energy difference between n plus 1 and n, and it's linearly growing with n. Now, it's inversely proportional to the size of the box squared. So when you make the box larger and larger, then the distance between the layers, between the levels, becomes smaller and smaller. For the macroscopic bodies, it becomes infinitesimally small because the bodies are large. and therefore you have a kind of continuum spectrum, right? Okay, that is all good, and this is kind of just a motivation that, okay, so for this case we can use particle in the box problem because well, we can consider the sodium electrons as now we presume that they don't interact strongly. That's an assumption that kind of physically feasible. All right, so then we have a large box, we have many electrons, the levels are somewhat separated, but with a very small distances between them. Now, where it goes very strange is the explanation now why sodium is a conductor. Okay, so why does it conduct? And the explanation goes like this. This is our sodium without electric field. All right, so these are occupied levels because we have more than one electron. So we have several, well, very many electrons actually in macroscopic sodium. And these are unoccupied, as we saw in the polyene problem, right? So we studied butatriene and butadiene, sorry. And we also looked at some other organic compounds. So there you have more electrons when you have a larger chain, right? Now, this is all good. Then we put the electric field. And what does electric field do to this problem is that it creates this inclination of the box. Okay, so it's exactly the problem that I just considered, the inclined bottom problem. Now, what he plots then is just the energy diagram with electric field, right? But this is nonsense simply because energy levels, they are constant numbers. They are coming as an eigenvalue of the time-independent Schrödinger equation. They are constants. No matter what potential is, the energies are constant. They don't have dependence on the kind of any coordinate, right? So, and then he says something like, okay, so that's his picture of like why sodium start conducting electricity because, their levels are somewhat inclined now because of the potential, and the electrons that are occupying the left-hand side, right, they are occupying orbitals which have a higher energy on the left than the same, I guess, type of electrons on occupied orbitals on the right-hand side, and then it's like very natural. It's almost like a classical liquid when you kind of tilt the glass, then you will get the motion of the liquid within the glass, right? So that's his kind of explanation, which is completely nonsensical from the point of view of quantum mechanics, because first of all, this picture is meaningless. Energy levels do not depend on the spatial coordinate, and then once this is meaningless, then it's not really clear how do you really go and connect this picture with the picture that, yeah, there is some conductance. Okay. All right, so this is just one of the examples where, and also insulators. So how do we understand why do insulators don't conduct? That's even less clear in this picture. Impossible to understand. All right, now how do we understand all this? Let me first use a board, and then I'll show you some simulations. Now, we know now how to predict quantum dynamics, right? We know the conductance phenomena is essentially a phenomena related to the motion of electrons from one side of the system to another, right? So therefore, in order to predict that some material will conduct, we need to solve time-dependent Schrödinger equation, okay, and prove that probability density which is observable quantity, right? Probability density for every electron is changing with time, right? So it's very natural. You put electric field in the conductor, you have this electron being here, after some time it should be there, right? So that's what you call conductor. If it's still there, then it's insulator. Means electric field doesn't move your electron. Electron stays where it was. You guys all asleep. Seriously, wake up. This is fundamental stuff. After this lecture, you can come home and explain to whoever you find there, or call your parents and say, now I understand why some materials conduct, right? On the most fundamental level, a quantum mechanical level, right? So, and you'll know what is wrong with the explanation, because I haven't seen a single book that explains this material clearly at the simplest possible level, because there are these books which kind of just simply wrong, okay? If we avoid political correctness, it's just simply wrong. And there are books that are right, but they are complicated. Like they are books usually from the condensed matter physics community, where they start talking about the electrons in the periodic potential of the material, and then things become a little bit more complicated. They ignore some, they don't ignore some of these periodic features, and things become more complicated. But my explanation will be the simplest and yet the right one. Okay. Well, you may of course argue about the second part. I will be happy to listen to your arguments, but at least it will be consistent with the rest of the course. Okay. So if we have a conductance, then the probability density must change with time. So when do we have that? When is our probability density changes with time? What can we say about the state of the electron? Can it be an eigenstate? It cannot be eigenstate, right? So what these all simplistic books ignore, they don't want to go into the difficulty of explaining what the superposition state is. But without superposition state, there is no motion in quantum mechanics. So the idea here is that you need to introduce superposition state at some point. And then things become very, very simple and kind of clear. Now, where do we get the superposition state? It seems like we're starting without electric field, with a particle in the box. And imagine we put and say we do things very simple. We put one electron in the ground state of a particle in the box. It has this profile, right? And the probability density, if you square this, will have, well, maybe slightly different, but similar profile. The tails will be kind of more. You will see it on simulation. They will be more compact, right? Then, all of a sudden, that's why I put delta t with a small delta, all of a sudden, you create the tilt of the bottom, right? And system, you may expect, instantly will not react to that instantaneous change of the profile, right? So you kind of turn on the electric field very quickly, and the system stays the way it was in the beginning. And then, what just changed? That's the question we may ask ourselves. What just changed? There was a Hamiltonian at the initial time, which is a Hamiltonian of particle in the box. And at time 0 plus delta t, we have a different Hamiltonian with the potential that has an inclination, right? So we have a different Hamiltonian. Well, h is different than h0, right? But we can imagine that the function we started with is exactly the same, right? Because we very quickly changed the potential. The function, we can say, is exactly the same as we started with. Now, this function, is it eigenfunction of this operator? That's the next very important question. This function was an eigenfunction of the Hamiltonian of the particle in the box. Function didn't change, Hamiltonian changed. Is this function still an eigenfunction of H? Now, new Hamiltonian. Well, most certainly not, right? Because simply H0 and H, they don't commute. We added the potential, and well, you expect that eigenfunctions of this Hamiltonian will be different. And indeed they are. I will show you in the simulations how different they are. Now, that means that the function we're dealing with is an not eigenfunction of the operator, Hamiltonian, right? But it's rather a linear combination of eigenfunctions. So it's a superposition state. So that's how we obtain the superposition state, that if we then expand as a linear combination of eigenstates for our new Hamiltonian, the coefficients will be not 1, 0, 0, but rather something. They can spread out over the eigenfunctions of our Hamiltonian, where we have an inclination due to the electric field. Electric field creates this potential, and these are eigenfunctions, but our state is not an eigenfunction, it's linear combination. Therefore, it will evolve in time, and that's the origin of the conductance, right? In this language, in language of quantum mechanics, using particle in the box, what happens is you kind of create the inclination. Your original function is not eigenfunction anymore. It is a superposition now, and it will start evolving. And that evolution, essentially in this system, will be back and forth, oscillations, right? That can be considered as a kind of illustration of the conductance. Now, more interesting, if this picture is right, it should also describe why do we have conductors and insulators, right? So where does the insulating property come from? Well, it turns out that if you start modifying the box, making it larger or smaller, the energy difference between the levels plays a crucial role in how much of the superposition this state is. It turns out if the levels are close to each other, and that corresponds to kind of closing the gap in the conductor materials, then these coefficients, they are spread out over very many states in this Hamiltonian. So our initial function is a true superposition that will oscillate back and forth very, very much, right? But if you make a box very small and the energy levels are very far apart, then it turns out that this function will 99% be an eigenfunction of the new Hamiltonian. And the oscillations you will see on the simulations will be very, very tiny. So that's the difference between semiconductor or insulator and the conducting behavior. The energy levels that essentially show us how many eigenstates are in this superposition, because for large motion you need many. And the sodium case is especially interesting. The sodium case, the occupied orbitals are not very, essentially not separated from unoccupied. And small change of the Hamiltonian will make the eigenstate of the untilted Hamiltonian a large superposition of the essentially tilted Hamiltonian. Okay, so now let's see some simulations. And all right, so first, eigenstates. Promise you to show eigenstates. Let's start with this. So this green is a tilted potential. This is a box from 0 to 10. The blue is probably familiar to you, ground state of the particle in the box. The red is a wave function for the tilted particle in the box, right? So with the tilted potential, you would expect the maximum to essentially shift to the lower energy position. Now, the wave function here is negative, here is positive. Is it okay? Well, technically, wave function is defined up to a constant. right? So that constant can be positive, can be negative. That doesn't have really physical meaning, because if you square this function, it will be positive, all right? So the main point here is that the maximum of probability distribution is shifted in the ground state. Now you can also look at this is the first excited state, because again the energy, the sign difference. You can see that the blue one is the normal particle in the box. The red one is the shift, with inclined potential, right? But the main idea is that it has one node, for the normal particle in the box, you have one node, and that is just to make the function orthogonal to the previous one, and also to increase the kinetic energy, because more nodes you have, more kinetic energy there will be. And here the fourth function, they both look very similar, red and blue. Blue is for normal particle in the box, and the red is for particle in the box with inclined bottom. Now let's see. This is the kind of initial setup of our problem. We have this wave function and no inclination in the potential, the green one, right? And this is time 0. Then I make an inclination, and I see what happens to the probability density. And as you would expect, it will start evolving. And because there is a barrier, not like in a normal conductor where you have you have wires to kind of accept electron, right? But here we have a box, and in that box there will be just oscillations back and forth. Okay. And again, just to emphasize, the reason why it oscillates is because we kind of made eigenstate superposition state by changing the Hamiltonian of the problem. Okay. Now, from the point of view of the coefficients, there are coefficients here printed out, and these ones. All right. So what I did is I expanded the original particle in the box ground state as a linear combination of eigenstates for the particle in the box with inclined bottom. And the first state has weight of 0. It's a coefficient, so you need to square to get the no, it's actually weight. So they all sum to 1. So the first state has a weight 55%, the second 40%, and then the third one is 5%, third is less than 1%. All right, so but there is some significant involvement of the excited state here, right? So the ground state of this problem is containing the excited state of the problem with inclined bottom, right? Because these are different Hamiltonians. Now, if we go back to the program, and now how do we make insulator out of this system that conducts so perfectly? How do we make the spread of states in the particle in the box problem bigger, right? So that's the idea. We can change the box length, right? But what I'd like to do, which is very counterintuitive, I want to change mass of the particle. Okay? You remember, for particle in the box, the energy levels are proportional to 1 over mass, right? Because the full expression is like this, right? So this is the full expression, and every energy level is 1 over mass. What does that mean? If we analyze the delta energies, it's always going to be 1 over mass, right? So what does that mean? The heavier the particle, the smaller the difference between energies, right? And the lighter the particle, the larger the difference between energies. Okay, so making particle lighter actually will make it go very short distance, which is very counterintuitive if you think about it, because you would expect lighter particle will move faster. It will move faster, but it will not move far. You will see now in simulations. Okay, so this is our original setup. It's our ground state. And now let's see. Yes, it does move faster, but it doesn't go far. Right? So it just essentially shakes around the equilibrium point. Right? And so there is no motion that we saw as like in the previous simulation. All right, and the reason for that, yeah, if we look at the weights of so essentially squares of these coefficients in the expansion, the ground state of the original problem is 99.99% is the ground state of this problem. So there is not much of the superposition formed. It's 99% the ground state, and the first excited state only contributes less than 1%. Okay, so that's why even if we do the tilt, if the mass is small and the levels are far apart, then this state is very much eigenstate of the Hamiltonian. The other states do not contribute to that superposition. It's still technically a superposition, but it's much closer to the eigenstate than in the case of bigger mass. Okay? So this is the interesting counterintuitive result. Of course, you can also change the L, but what I don't like about changing the size of the box in this problem is that, well, then changing the size of the box creates, because our electric field grows with the size, you kind of a little bit cheating by making a bigger box. The field will be also bigger eventually if you consider fields at the different sides of the box, right? Because the box is larger, field grows linearly, right? So, but here with the mass, it's very clean indication that okay, the superposition is the key, and the superposition builds up much better if you have a heavier mass. Okay. All right. So with that. I guess we're done with the simulations. Any questions? All right, if no questions, then I'll start a new topic, and that will be kind of summarizing what's the big picture here, and how can we use these approaches to go and study molecules, because that's what chemists want, right? This is all kind of only useful if we can apply it to molecules and get some insight. Well, the good news and the bad news. The good news is that this all can be used in a very approximate way to get some insights. But when we want to kind of apply it rigorously to molecules, then things are becoming very, very complicated. And in this course, we won't be able to cover rigorous theory of the molecule using a quantum language. We always will be kind of talking about approximations. Right? And maybe that kind of makes me think maybe quantum mechanics is something that needs to, well, maybe it's something intermediate. Maybe eventually we'll have something simpler and more powerful. Because right now, don't get me wrong, all this stuff, if you make computer do the work and the calculations, right, it produces very accurate results which are comparable to experiment. So you can predict spectra of molecules, any property. It just the language, like if you ask then yourself, okay, why does computer produce me these results that match experiments? You start looking in the code, looking at the intermediate quantities. First of all, the number of quantities is so big that it's like talking about that would take a long time, and the number of equations is just big. There's no really simple compact picture like I'm showing you with the particle in the box. It's very short and kind of compact, but it's approximate. Now, if I try to do the full formalism, then things become very difficult very quickly, and if you thought that what I presented so far was difficult, yeah, I think what I'm about to present will change your views. Okay. All right. So, but I wasn't given any other mechanics but quantum mechanics, so that's what I'm gonna teach you to the best of my abilities. All right. And maybe one day you'll come up with something better. Now, the idea here is we talked about particle in the box, and I want to give you a flavor. How do we go from particle in the box to a real molecule? All right. So, what will be the Hamiltonian? What will be the time-independent Schrödinger equation? And that's essentially the problem that electronic structure or quantum chemistry, that's the problem that quantum chemistry solves. Okay? And so that you can see what type of problem do we need to solve in order to predict properties of molecule from first principles. Right? So if you can solve time-independent Schrödinger equation for molecule, then you can access any property. You don't need to go to the lab. You don't need to do the IR, NMR, or whatever spectra, right? So you can have all the spectra just out of the computer, which solves the time-independent Schrödinger equation. So it's very powerful, I think, by just construction, what I'm about to say, but it's also hard to do. All right, so very ambitious project. Now, what we'll be using is atomic units, where h bar, mass of electron, and absolute value of the charge of electron is all 1. So this is atomic units. Atomic units. It just makes the formulation simpler. And I'll tell you about molecular Hamiltonian. Because if you want to use quantum mechanics to any system, well, the first question is, what is the Hamiltonian? You don't know what the Hamiltonian is, there's nothing to talk about, right? So that's it. Like the equations that quantum mechanics requires you to solve, they require formulation of what Hamiltonian is. All right, so we start talking today, and we'll continue next lecture, although next lecture there will be midterm, then lecture after. All right, so molecular Hamiltonian. There is nothing new here in a sense. Actually, one thing I want to say from the beginning, formulating what the Hamiltonian is the easiest part of the quantum mechanics, right? So that's the easiest part, writing the Hamiltonian. It's very straightforward. I'll teach you how to write it for for any molecule, any atom of periodic table. You can write a Hamiltonian easily. Solving the equation, that's the hard part. which hasn't been done yet, or it's almost kind of impossible to do. It's impossible to do analytically. Numerically, it's very hard. All right, so why is it very straightforward? Because, well, any Hamiltonian has a kinetic energy and potential energy. So no news here. So you have kinetic energy of all particles and potential energy of all particles. Now, what kind of particles do we have in molecules? Elementary particles. Kind of not elementary, but particles. I realize only electrons are elementary because we don't go into the nuclei, right? So molecules have electrons and nuclei. And nuclei, they are not elementary. They are formed of by nucleons, which are neutrons and positrons, right? But neutrons and positrons, they are connected by weak force, and we don't go there. Like, it's essentially, for us, nucleus is something that is elementary in a sense. We don't go further. So the particles are electrons plus nuclei, right? And so for electrons, we know that they have mass of electron, and okay, so mass of electron is 1, and charge of electron is -1. Nuclei, they have mass m alpha, which is much bigger than the mass of electron, and they have charge z alpha, which is not much bigger, but still, well, it's positive, and it's bigger than absolute value of the charge of electron. But that's not essential, not very essential. This is more interesting because the fact that the mass of nuclei are heavier than electrons allow to use some approximation for nuclei as classical particles, while for electrons we cannot do that. But we won't go much into that. Now, all right, so how do we write down kinetic energy? Naturally, it's kinetic energy of electrons plus kinetic energy of the nuclei. Again, very straightforward, right? So you have electrons, nuclei. And then we have three-dimensional space, right? So no escape from that. Therefore, all electrons are indistinguishable. We'll talk about this more. They are essentially, at the level of the Hamiltonian, they are identical. Okay? And therefore, we have Hamiltonian we enumerate electrons by subscript I, n with subscript e is the number of electrons. And if all our electrons would live in the 1D world, one-dimensional world, then the kinetic energy for them would be just a sum over second derivative with respect to x. But we have y and z coordinate, right? So therefore, we have other derivatives, like we considered the 1D particle in the box, 2D particle, 3D particle in the box. So this is like 3D particle in the box. Now we have more than one particle. We have number of electrons particles, right? So the interesting thing which you may find confusing about the quantum mechanics, or I would say one of the confusing parts about quantum mechanics, is that you really cannot distinguish, if you just look at the Hamiltonian, and mathematically this is kind of the same thing, whether you have, say, two particles in one dimension or you have one particle with 2 dimensions, right? Because the number of coordinates grows like 3 and e, and then if you consider one electron in, let's say, if you consider 3 electrons in 1 dimension, you can have the same Hamiltonian as 1 electron in 3 dimensions. Because these coordinates x, y, and z, this can be coordinates of 3 electrons in 1 dimension, each in 1 dimension because they're independent, or this can be coordinates of 1 electron in 3 dimensions. So mathematically, the problems are equivalent at the differential equation level. Anyway, so this is the kinetic energy of electrons. And for short notation, sometimes this operator is called Laplacian. Right? This is a sum over second derivatives for a particular electron. And then the whole thing can be written in atomic units as very simple. H bar is 1 in atomic units, mass of electrons is 1 in atomic units, so it's 1/2 of the Laplacian with minus sign, right? So that's the whole kinetic energy. Now, kinetic energy of nuclei, right? Okay, so this thing has more terms, more interesting terms. It has masses of all nuclei. And it has Laplacian over, essentially, nuclei will have their own coordinates. Let's call them with big, small x, y, and z, and there's big x, x alpha, and z, right? So every particle in quantum mechanics has three coordinates at least. If we don't go into spin, which we won't till the end. And so for now you can just think that every particle has 3 coordinates. Okay. Now we set up what the kinetic energy is. Now let's talk about the potential energy. So we're dealing with charged particles, right? And charged particles have what interaction between them? Plus, minus, plus, plus. What do they do when you bring them together? That's right. So what's the name of this? The guy in what, 18th century who came? Coulomb. That's right. So there's a Coulomb interaction. And so then we will have potential term that contains electron-nuclear attraction, electron-electron repulsion, and nuclear-nuclear repulsion, right? So 3 terms. One attraction, 2 repulsions. All right, now let's start with repulsion, electron-electron. It's 1/2 I not equal to j 1 over Ri, Rj. Okay, so we enumerate all the electrons, right? we consider all pairs of I not equal to j. Every electron has its own coordinate. So this is our coordinate system, x, y, z. And we are thinking about electron coordinate as R, say, 1, which contains x1, y1, z1, right? This is a vector, and say electron 2 also has a vector, and Coulomb repulsion energy depends how close these 2 points are. Okay, and the distance d12 is given by this expression, r1 minus r2 absolute value. What does this mean? If you subtract one vector out of another vector, you get a vector. So you can think of this as a vector, right? The distance between the difference between r1 and r2, if you consider it first as a vector, then the distance itself is a number. So we are getting a number when we take this difference vector and take the absolute value of it, right? So algebraically, this should, well, boil down to the equation that you already probably saw. The distance between 2 points in 3D or 2D is generalized from 1D by taking the differences between the corresponding coordinates, x, y, squaring them, and summing the squares, taking square root. Okay? You can kind of think about this as a Pythagoras theorem, right? So in 2D, that just comes out of that. And in 3D, it's just generalization. Okay, so that's the distance, and the smaller the distance, the bigger the repulsion. Okay. Now, electron. Okay, so same type of term can be written for the repulsion of 2 nuclei, right? Only now that we have charges of corresponding nuclei and their coordinates. Okay. All right, and then attraction. It will go with minus sign because it lowers the energy. Okay. So that's pretty much all terms that you need to consider in time-independent Schrödinger equation. Say if you have H molecular, then it's T of electrons, T of nuclei, plus Vn, Vnn, plus Vee. So that's the Hamiltonian. And then this is time-independent Schrödinger equation. Okay. Now, what I want to emphasize is that molecular function is a function of very many variables. Okay, if we just count number of variables, 3 times number of electrons, 3 times number of nuclei, right? So that's the number of variables that we need to consider, and that's why quantum mechanics is so computationally expensive, because the functions that we need to operate with, they're kind of the arguments, they grow linearly with the size of the system. But in order to find the functions, we're only given the differential equations. Okay, and to solve differential equations for increasingly number of dimensions become well kind of much harder, well very quickly, and the computational cost grows exponentially, essentially. Now, one way to see all that is that if you asked to characterize a function, right? So if I say gave you some function f of x in one dimension, right? And I didn't give you the analytical form, just a plot, right? And you somehow want to store this information on a computer, right? So what would be natural way to store it? You will have a grid of points, right? And for every point, you store, well, where this point is, and you also store what the value of the function was for that point, right? So you have, say, if you have 10 points, which just makes my math simpler, right? 10 points, then 10 values. So you need to store 10 points and 10 values. So together 20 points to store. Imagine we go into the two-dimensional world where we have two coordinates, x and y, and I gave you a function again. That's kind of form some kind of surface, right? Then, following the same recipe, you put 10 points along each dimension, 10 on x, 10 on y. Only now that in order to store all the values, you will have 10 times 10, 100 points, 100 values, and number of points that you can maybe not store really. Just number of points is really cheap because all you need is like x mean, x max, and the delta, right? Presumably. So we may skip counting number of points, but number of values that you need to store still from one dimension to two dimensions grows exponentially because the dimension goes into the exponent, right? Not into the 10 is staying, right? So if you want to say more accurate representation, you may put 100 points, but if you put the 100 point in one dimension, then it will be 100 times 100, 10,000 in two dimensions. Now imagine going to the 3 dimensions, right? 4, and very simple example of, say, if we consider methane, right? What is the number of electrons in methane? $16. No, it's smaller. It's only 10. Right, so we have 1s2, 2s2, 2p4 for carbon, plus 4. I guess chemists. All right, so 10 electrons. And how many nuclei? Are you using calculator for that? How many nuclei do we have in the methane? Do everyone agree? Good. For a moment I start worrying. Right, so 5, because it's 1 carbon and 4 hydrogen, right? So that's what this formula is telling us. 5. So together, 10 plus 5 is 15. Great. So 15 multiplied by 3, that's the number of variables, right? 3-dimensional world. 15 times 3, 45. Okay, so if we decide to use 10 points per dimension, this is the number of points you need, 10 to the 45, to describe molecular wave function for one of the smallest molecules, right? So someone made a calculation that if you transform all this into the terabytes and DVD disks, right? So that's the kind of common way of storing information. Say, if someone gave you a wave function for the methane and said, okay, store it now. So how many DVDs do you need to store this wave function? It turns out that if you turn the whole kind of Earth into the DVDs, there will be not enough DVDs to store this, right? Because the information is just too much, right? So even if you turn all the atoms that are available from the Earth into the material that makes DVDs, right, or essentially make it for the very efficient into the media that will store, and even then you won't be able to store all this information. All right, and that's only for the methane. That's why the quantum mechanics is powerful, and it kind of describes a lot of things, but the language it uses is not always very economical, right? So we need approximations, and that's the active area of research. How do we build approximations so that we won't need to store 10 to the 45 in our computers? Okay, but about approximations we will talk next time after midterm.